All right, sound check done. Let me put away the headphones again. And welcome to the office hours section of the stream. Let's go ahead and see what's on our agenda for today. I mean, I already explained it for those who showed up for the earlier part of the stream, but we are continuing with the topic of Riemann sums from last week. So I did figure out why this did not come out to what I was expecting it to be. I was expecting to get 1/3 b cubed minus a cubed, but the reason I didn't get that is because let's see, which page was it on? Was it on this page? Yeah, it was because I plugged in a equals 0 and I eliminated those two terms. So if those two terms had been included, then that would have added enough stuff in here to then cancel a bunch of the things that I get from foiling b minus a cubed. And that would have resulted in 1/3 b cubed minus 1/3 a cubed, which I think I'm going to go ahead and do because we might as well. It doesn't hurt. Maybe it'll help with checking my work too and make sure that my work from before was done correctly. So let's see. If I add these terms back in, then, well, we already took care of this term last time. This term, when we took the limit of it as n approaches infinity, we ended up with this thing, which was b minus a all cubed over 6 times the limit as n approaches infinity of 2 plus 3 over n plus 1 over n squared. The 3 over n and 1 over n squared went to 0, and that just multiplied the 2 into our 6, reducing it to a 3. The 2 into our 1 over 6, reducing it to 1 over 3. So yeah, that third sum is already taken care of. Let's take a look at these other two sums. So limit as n approaches infinity, let's see. Limit as n approaches infinity, I'll do one term at a time, of, what was it again, a squared delta x? Yeah, a squared delta x times the sum from I equals 1 to n, yeah, from I equals 1 to n of 1. Well, what is this sum over here? I would do 1 plus 1 plus 1 plus 1 plus 1, how many times? Up until I've added 1 n times. So n ones would add up to a total of n. So this simply becomes limit as n approaches infinity of a squared times our delta x was what again? It was b minus a over n, right? Delta x was b minus a over n. Just double checking and making sure I didn't define it differently anywhere here. Yeah, delta x is b minus a over n. Limit as n approaches infinity of a squared times b minus a over n times this sum just becomes an n. Well, these n's cancel out. And so I'm left with a squared times b minus a, which is independent of n, so this just becomes a squared b minus a squared a, which is a cubed. Okay, so that's our first term taken care of. Now for our second term, 2a delta x squared times the sum from 1 to n of I. Our next term is limit as n approaches infinity of, I've already forgotten, 2a delta x squared. Yeah, 2a delta x squared, sum from 1 to n of I. Well, we talked about this sum before. If you just add the numbers, first I equals 1, then it's 2, then it's 3, 1 plus 2 plus 3 plus 4. We talked about that last time. We said that this sum is just equal to n plus 1 times n all over 2. So we can go ahead and make that substitution and also substitute the delta x while we're at it. So we get limit as n approaches infinity of 2a, and then delta x squared is going to be b minus a quantity squared over n squared times, that sum becomes n times n plus 1 all over 2, right? Did I copy that correctly? N plus 1 times n over 2, same thing. Okay, one of the n's cancels out there. The 2, this 2, cancels out with that 2. And then n plus 1 over n. Well, I can factor out the a and the b minus a squared, so a times b minus a squared can be factored out of the limit since they don't depend on n. And I see the sniffles are coming back from before. Sorry about that. I hope that doesn't get too annoying. And we've got, what's left inside? N plus 1 and n in the denominator. So n plus 1 over n. That's going to be n over n, which is 1, plus 1 over n. N plus 1 over n reduces to n over n plus 1 over n. And 1 over n, as n goes to infinity, 1 over n goes to 0. So this limit just becomes a 1, which means we're just left with a times b minus a squared. Okay, now we have all the pieces we need, and those sums were all just, added to each other. So let's go ahead and add these terms to that term and see what we end up with. It should be 1/3 of b cubed minus 1/3 of a cubed. Oh my goodness. Out of all the times that my nose decided to act up. Okay, hopefully that'll do it. Okay, so we had 1/3 b minus a cubed. Well, let me write them in order. So this term was first. So if I had done this without dropping those two terms at first, I would have had them as a squared b minus a cubed plus this a b minus a squared, which I will expand in a minute, plus this 1/3 of b minus a all cubed. Let's see what we can do with this. So that doesn't need any more simplifying. This becomes a times, let's see, b squared minus 2ab plus a squared. So that's a times b squared minus 2ab plus, a squared. Not b squared again. That would have been a fatal mistake right there. Okay, plus 1/3. Let's copy that over. a squared b minus a cubed. Okay, b minus a all cubed. I'm gonna start with b minus a squared and then multiply it by b minus a. What was it? It was 1, 3, 3, 1, but I don't want to take shortcuts here. I'd rather do it slowly and carefully, especially since some people might not know that shortcut. So I'm going to do b squared minus 2ab plus a squared, that's just b minus a squared, times, we've got one more b minus a. And if we multiply the b minus a into this, first of all, is there anything that cancels among these terms? I would hope so. That can reduce the amount of writing I have to do here. I see a minus a cubed, and if I distribute this a, I'm going to get a plus a cubed over there, so plus a cubed and minus a cubed, those will cancel out. A squared b, well, when I multiply the a into here, I'll get minus 2a squared b, but other than that, not much. Let's see. A squared, let's see, a squared b. I'll write the ab squared, actually, yeah, I'll write the ab squared first. So ab squared from here. And then minus 2a squared b plus 1a squared b. Minus 2 and plus 1 is minus 1a squared b. And that's all that's left of those two terms, it looks like. Plus 1/3 of, here we go, b times all this stuff, so that's going to be b cubed minus 2ab squared plus a squared b and then minus a times b squared, so minus ab squared, and then minus a times minus 2ab is plus 2a squared b, and then plus a squared times minus a would be minus a cubed. Did I do all that right? So distributing b, I get b cubed minus 2ab squared and plus a squared b. Distribute minus a and I get minus ab squared plus 2a squared b and minus a cubed. Okay, that is all looking good. Is there anything in here that cancels out? Well, I have like terms that combine. I've got a squared b combines with 2a squared b to make 3a squared b. So I've got 3a squared b, and I've also got minus 3ab squared. So I've got, copy those over, a b squared minus a squared b plus 1/3. I've got the b cubed, and I'm going to go ahead and write the minus a cubed. And then for these in-between terms, I've got minus 3ab squared and plus 3a squared b. And if I multiply each of those by the 1/3, if I distribute the 1/3 to them, then I get minus ab squared over here, which cancels out with the plus ab squared. This ab squared cancels out with minus 3ab squared divided by 3. And similarly, 1/3 of 3a squared b minus the a squared b on the outside, those also cancel out. And I do indeed end up with 1/3 of b cubed minus a cubed. Okay, perfect. That is what we are supposed to get. And of course, if you plug in b equals 3 and a equals 0, we still end up with 9. But now that we have it in this format, now that we have it in the proper format, it will work even for cases where a is not 0. So this over here, this 1/3 b cubed minus a cubed, this can be represented as the original function we started with was the function f of x equals x squared, and we were calculating the area under its curve from 0 to 3, from a equals 0 to b equals 3. So we represent this in calculus as the integral from a to b of the function x squared integrated with respect to x. Integrated with respect to x. And did I actually show that last time? Yeah, I did that over here. So this dx, we know the variable we're integrating with respect to is the variable for which we take really small deltas, or, well, in this case we had pretty big deltas that became really small when we took the limit where n approaches infinity. But yeah, those really small deltas basically turn into this dx in the integral form of this sum, and the integration bounds, the interval over which you're calculating the area, become the bounds of this integral. And then inside of that, you have this function. So official terminology, this dx thing is called a differential. That dx is called a differential. It tells you what your variable of integration is. The function that goes inside of the integral is called the integrand. Which might not be too foreign to you if you know, for example, that the numbers in a multiplication are called multiplicands, or the number being divided in a division problem is called the dividend. It's that kind of terminology that we're looking at. So when setting up integrals, the thing that you need to remember is that the variable of your integrand must agree with the variable indicated by your differential. Otherwise, you can't really do anything. I won't go over a proof of this rule, but the basic idea for at least polynomial functions is that to do their integrals, all you have to do is increase the exponent by 1, so x squared becomes x cubed, and then you divide by whatever that new exponent is after you've done that increase. So if the 2 becomes a 3, we then divide by a 3, and you get x cubed over 3. Then what you do is you substitute the upper bound and the lower bound, and you calculate the difference between those two. So let me actually write that out on a new sheet of paper. Let's go ahead and write that out on a new sheet of paper. Integral from a to b of x squared, getting ahead of myself, with respect to x, is equal to, we would call this x cubed over 3 from a to b this basically means we take this x cubed over 3, we plug in b first, so it becomes b cubed over 3 minus, and then we take this expression again, but now we plug in the lower bound for x. And there you go. That's the basic idea of how to deal with these integration bounds. When an integration has bounds, it is called a definite integral. So this is an example of a definite integral. When an integral doesn't have bounds, that's called an indefinite integral. It has multiple possibilities for what it could be, because you're basically doing the opposite of a derivative, except a derivative is a one-way process, while the integral is not a one-way process, because there's more than one function that has the same derivative. If that doesn't really make sense to you because you haven't had any calculus yet, you might want to look at that stuff first, but you don't really need it for what we're going to do today. I'm just, providing some extra information here. So I guess what I want to do now is just give you a general formula for the integrals of polynomial functions. If I'm doing an integral of a polynomial function, I'm not going to write bounds this time. If I am going to find bounds my brain is thinking faster than I can talk. Let me slow down. I want to write the general formula for the integral of a polynomial, or at least a polynomial term. So if I have x to the n, if I'm taking the integral of x to the n with respect to x, then the formula for that is, as I described earlier, you increase the exponent by 1, and you then divide by that new exponent. So the new exponent is n plus 1, I divide by n plus 1. And then this is something from calculus class. You also have to add a constant here, because the idea is that this is the reverse of a derivative. The idea is that this is the reverse of taking the derivative of a function. And if you take the derivative of a function, again, sorry if this sounds foreign to you, but for the people who know derivatives, you might want to pay attention to this. If I did something like the derivative of x squared plus 5, and I also did the derivative of x squared minus 12, and I did the derivative of x squared plus 107, and I did the derivative of x squared minus 382. All of these functions will have the same derivative. All of them will have a derivative of 2x. All of them will have a derivative of 2x. So if I want to undo that derivative, then let's see, x to the first power becomes x to the second power, so 2x to the second power, and I divide by that new exponent, 2, and so those 2's cancel out. So I've got back my x squared, but I also have to put in this plus c here, and I don't know what this c is. It could be 5, it could be negative 12, it could be 107, it could be negative 382. There's multiple functions that have the same derivative, so when I reverse the process, I have to pay respect to the fact that I have multiple possibilities for what this function could actually be, and I would need further information to determine the actual value of this c. For the students who haven't done derivatives, don't worry too much about this. Just know that this is something you need to include when you don't have integration bounds. Technically, you could still include it if you have integration bounds, except the problem is it just disappears. If I were to go back here, for example, if I were to go back here And instead of x cubed over 3, I did x cubed over 3 plus c. If I did x cubed over 3 plus some constant evaluated from a to b, then what that would mean is I would take b cubed over 3 plus whatever that constant is, minus a cubed over 3 plus whatever that constant is. The constant cancels out. So when you have a definite integral, when you have an integral with clear integration bounds, you do not need the constant of integration. It just cancels out. But if you have an unbounded integral, if you don't know what your integration bounds are going to be ahead of time and you're just trying to derive a general function, you need more information. Otherwise, you have to put your ignorance on display by including that plus c. And I mean put your ignorance on display in the literal sense, not in some sort of I don't mean it in the sense of like embarrassing yourself. I mean just being honest about the fact that you do not know. Anyway, we're not going to worry about that too much. Instead, we are going to now try and apply Riemann sums to something more than just what we did last time, which was rectangles. There are other sorts of things that we can chop things into. So let's do the derivation of the volume formula for a cone. Volume of a cone. Let's see if we can make sense of the volume of a cone. So let's draw a cone. Looks something like this, and then has a circular base. It goes something like that, right? It's going to have some sort of height. I'm going to call that capital H. I will not specify what this height is, but it is a constant. That's the key thing to remember. Whatever this height is, sure, it's unknown, but it's also a constant, not a variable. Just because something is unknown doesn't mean that it's automatically a variable. Similarly, I want to define the radius of the base of this cone as capital R. Again, a constant. I'm trying to derive the general formula for the volume of a cone, which, regardless of its base radius and height, will always be, as we were taught in geometry, volume equals 1/3 pi radius squared times the full height of the cone. That's the formula we were given, but we were never taught where this formula even comes from. Well, today is the day that we try and prove this formula. Today is the day. Let's grab the orange pen for this. So, similar to how I calculated the area under the curve of x squared by chopping the area into smaller, more manageable pieces, namely rectangles, I want to do the same thing with a cone. I want to take a cone and chop it into pieces that are simpler to deal with. What is a simpler shape that I could chop a cone into that approximates the volume of a cone? What would that be? Well, if I chop it horizontally into its cross sections, then I end up with something not too different from a stack of discs that have successively smaller and smaller radii as I progress to the top. And I think I actually want to draw the top first. Yeah, something like that. And then next disk will be something like that. I know I'm taking my sweet time with this, but I think it's worth it. And maybe, yeah, one more. If I were to take a stack of these, what would I call them? Really short cylinders. We refer to them as disks, but they're also cylinders. If I were to take a stack of these disks and calculate the volume of each individual disk and add them up, they do approximately look like they would add up to the volume of this cone, especially if the combined height of the disks was equal to this capital H, and if the radius of at least the lowest disk is still capital R. This looks like it might give me a somewhat decent approximation of the volume of a cone if I added up the volume of these little disks. So what if I sliced these disks thinner and thinner and thinner, and I just stuffed as many disks as I could? Like if I stuffed more disks between the ones I've already drawn, and then even more disks between those disks, and so on and so forth. If I just did this as much as possible, if I tried to get a near infinite number of disks, making them practically razor thin, then you could argue by the same logic that we used over here for rectangles. The thinner we made the rectangles, the better the approximation of the area became. Well, the thinner the disks are, the better their total volume approximates the volume of a cylinder. So let's see if we can come up with some sort of relationship that determines the volume of an individual disk. So each individual disk is going to have a small piece of the total volume. Each of these disks is going to have a small piece of the total volume of this cone that we're trying to figure out. The volume of a disk. The volume of a disk is going to be, let me draw like a zoomed in picture of one of these many disks. This disk is going to have a radius little r. I'm not going to call it big R because only the bottom disk is going to have a radius of big R. All the other disks are going to have radii between big R, and then I guess the topmost disk will have a radius of basically 0 to represent the tip of your cone. So I'm going to use little r for the radius of any random disk within this stack. It's going to have some sort of height that's going to be a segment of this total height. I'm going to call this delta h in a similar manner to how I used delta x for the widths of my rectangles that spanned some larger interval along the x-axis. Here, I'm going to give each disk the same height, the same delta h, and I'm going to make the disks so thin that these delta h's become negligible, in much the same way that I had my delta x's for rectangles become negligible by just creating more and more rectangles. So if I know these two things, then the volume of any given disk is going to be the area of the base, pi r squared, it's just a cylinder, times the height, which I'm going to call delta h. So the volume of an individual disk is going to be pi r squared times delta h. where do we want to go from here? Well, we need to define an interval over which we are stacking our disks. We need to define an interval over which we are stacking our disks, and a good way to do that is to draw our cone sideways and superimpose it, that is, lay it against a coordinate system. So let's do this. Let's do a side view of the cone. And a side view of the cone is going to look like this. So this is a side view of the cone. It's going to have this distance be equivalent to the height of the cone. So I guess our delta h's would be just little sections of this horizontal axis. And then any random distance from this axis to a point directly above it or below it, that would be a radius. That would be the equivalent of the radius at that point. Okay, so it looks like our h variable is going to be from the value of 0 to the value of capital H. It looks like we are working from, it looks like our h goes from 0 to capital H. We could also think of it in another way. We could think about it in terms of radius. So let me see, do I actually want to rotate this? I suppose I could do that. Yeah, if we were to rotate this view 90 degrees, so if I were to draw another coordinate system, another way we can think about this, I did it wrong. I'm supposed to make this one longer. Another way we can think about it is we can look at the cone, again, sideways, but I'm going to look at it, I guess I'll look at it upside down. We could also think about it as the radius being on an interval. That should be symmetric, but I drew it poorly, where the radius starts at 0 and goes to a maximum of capital R over here. We could also think of our radius as existing on an interval from 0 to big R. You can actually solve this one in two different ways, depending on which of these perspectives you want to take. I want to take the perspective that we are actually going to be stacking these from a radius of 0 to a radius of big R. I think that might be the better way to go about it. Well, I'll think about it some more. Let's just keep moving with this formula, and then we'll decide whether we want to define our bounds in terms of h's or in terms of r's. Let me see. So the volume of an individual disk is equal to pi r squared times delta h. If I were to my mind is drawing a blank. I even rehearsed this. Man, after all that prep time. Like, I know the outcome that I'm supposed to get, but what I'm struggling with right now is how to explain it in terms that are easy to digest for somebody who's learning it for the first time. Yeah, I'm not sure. let me just proceed with this. So let's pick out a random disk from this sort of side view that I drew over here. And I guess we'll pick out this as our random disk of choice. There's going to be some sort of delta H associated with it. We're going to multiply that delta H by pi and whatever this radius is squared. And I want to come up with a relationship between R and H. I want to come up with some sort of relationship between R and H that will help me determine how R changes with H or vice versa. So what I can do is I can just draw similar triangles, or similar cones, if you will. I will do that over here. So let's say I draw two cones, two triangles, however you want to think about it. Let's say I draw a second cone over here. And this second cone, its base is going to have some radius r, while the main cone has a radius of big R. This little cone is going to have a height I'm going to call little h, while the full height of the cone is big H. And if you remember your geometry, you remember that similar figures have equal proportions between their dimensions. That wording is probably confusing, but you can probably intuit that little h over big H is the same ratio as little r over big R. Little h over big H is equal to little r, is equal to little r over big R. And we need this. We need this because otherwise we're going to run into a problem. So when I want to figure out the total volume of this cone, if I want to approximate the volume of the cone using these disks, then I want to calculate the sum of a bunch of pi r squared delta H terms. I would want to express either the H in terms of R or the R in terms of H, because when I turn this into an integral, it's going to become the integral of, I guess, our delta H is going to become a dH over here, and this is going to become the integral of pi r squared dH. This is hinting back at what I was saying earlier about the integrand and the differential. Where was it? Right here. Your integrand and differential need to agree with each other. I cannot do this integral as it is right now because my variable r is not defined in terms of h. So I either need to change this differential or I need to change this variable. We haven't really learned how to change differentials, so I'm going to focus on changing the variable. Fortunately, we've got this, so we can redefine r as, let's see, I'll do it over here. Just multiply the big R over to the left, and you've got little r is equal to big R over big H times little h. Okay, and now we can substitute that in for our r, and that gives us the integral of pi big R over h times little h dH. Okay, I guess we have to define our integration bounds now. Since we are integrating with respect to h, our integration bounds should be in terms of h. So I guess we are integrating from h equals 0 to h equals big H. So our integration bounds are going to be from 0 to big H. Now, the pi, the big R, and the big H, those are all constants, and they're not really going to affect our integral. They're not really going to affect our integral. We can factor them out. They are independent of our variable little h, so they can just be factored out of the integral. Kind of like if you were to imagine, if I were to go back to this graph of x squared, and instead it was a graph of 2x squared or 3x squared, some constant times x squared, then all that would do is it would multiply the heights of all the points by whatever that constant is. So if it was 3x squared, each of these rectangles would be 3 times as tall, but they would still have the same width, so they would end up having just 3 times the area. 3 times the height with same width would give you 3 times the area. So multiplying your function by a constant has the effect of just multiplying the end result by that same constant. That's all it really does, so I can factor it out of the integral and save it for later. I can factor out pi big R over big H, and now all I have to do is the integral of little h with respect to h. Okay, so this is just a polynomial function. It's h to the first power. I can just follow this formula. By the way, this is called the power rule of integration. I can just follow the power rule and say, when integrated, this h becomes h to the 1 becomes h to the 2 divided by that new 2. So it's going to give me, let's switch colors, and I don't even think I can fit it all in here. I might have to write it on another page. I'm left with pi big R over h times h becomes h squared over 2, and that is going to be evaluated from 0 to big H. Equals pi big R over big H times, I guess it'll just be big H squared over 2. Hold on, did I do something wrong? I did do something wrong. I'm seeing it now. Okay, I screwed something up. I forgot to square my R. I forgot to square my R. This big R over big H times H needs to be squared. Okay, let's do that on the backside. Let's start that over. So we had integral from 0 to big H of, we had pi r squared dh. R squared becomes big R over big H times H all squared dH. Did I copy that correctly? Big R over big H times H. Yep. Okay, now this becomes, I'll factor out the pi, and that becomes big R squared over big H squared times little h squared dh. I'll factor out the big R squared and the big H squared. Pi big R squared over big H squared times the integral from 0 to h of h squared dh. Okay, now we're back on track. This is going to become h cubed, and then we're going to divide by 3. So that's going to be pi r squared over h squared equals h cubed over 3 evaluated from 0 to big H equals pi big R squared over H squared times big H cubed over 3 minus 0 cubed over 3. Well, the 0 doesn't add anything, so we're just left with this big H cubed. H cubed reduces with H squared to just an H, and all that's left is pi big R squared big H over 3. Or 1/3 pi R squared H. That is the volume formula for a cone. Now we could do a thing where we change the variable of integration. We could change this dH into a dr, and that actually still uses this over here. We could do that, but I don't want to introduce that idea to students who may not have done the U substitution rule, because it's going to look very foreign, and I'm not sure how I would properly explain it to someone who hasn't had that calculus experience yet. But there you go, that's the volume of a cone through stacking the volumes of a bunch of disks. I skipped the phase where we actually set up an approximation. I just kind of wrote an incomplete summation over here and just basically implied that it leads to this, it implies this. And I hope you can see that from, I think I showed it last time, did I not? Where was it? I know I had something around here somewhere. Where was it? I could have sworn. Wait a minute. Where is it? Oh, there it is. Yeah, I even pointed to it earlier today. Yeah, your sum basically takes your, if you're calculating a sum where you've got a function times some sort of delta, your delta eventually turns into this differential, and the function that you're summing just becomes the integrand. It is kind of hand-wavy logic, but without teaching you a full calculus course, I think that's the best I can give you for now. So how about we move on to something else? How about we try and apply the idea of Riemann sums to something else? How about a problem that we run into in physics sometimes, where you might have an object with a variable density. Let's say, for example, that we have, let's say we have a sphere. Let's say we have a sphere. And let's say this sphere has a total radius of big R. And let's say that the mass of this sphere is not distributed evenly. Let's say that the mass of this sphere is not distributed evenly. What if we had a sphere where it had no mass at the center and its outer shell was the densest part of it? So it's the least dense at its center, and it gets heavier and heavier and heavier as you go outward. How would I describe the mass of this object? let's say that the density varies linearly as you move out of the radius. So sphere with density that varies linearly. Probably not the most useful example for mechanics, but for electricity and magnetism, you might see something like this. It would be a charge density rather than a mass density in that case. But yeah, a sphere with density that varies linearly with increasing, that varies linearly with r, that varies linearly with radius. I would describe this as having something called a density function. I would say density, in this case, the symbol for density we're going to use is the Greek letter rho. That's what's commonly used in physics. Rho, as a function of r, is equal to, let's see, if it varies linearly with r, then I'm just going to say it's a constant. Let's call that constant k, times r. Seems simple enough. When r is equal to 0, density is 0, so there's no mass at the center. When r is equal to, I don't know, 2, then it's whatever this k is times 2. Okay, let's find an expression for the total mass of this object. So let's find an expression for the total mass of this object. M total mass. What would it be? In case you've never really worked with density before, in case you haven't had chemistry, or physics 2 would be the other place you encounter the concept of density, let's do a quick briefing on what density is. So, for a lot of objects in the world, you're going to see they're just made of one solid material, and their density is just evenly distributed throughout the volume or area or length of that object. If I have, for example, this ruler, I would assume if I chop it up into pieces that are 1 inch long, I would assume each piece weighs the same. I would assume each piece has the same amount of grams per inch of whatever this material is. If I had like a block of wood and I sawed it and diced it into little pieces, I would expect equally sized pieces to have equal masses. That's what we call a uniform density. That would be when the density is just equal to a constant. That's not what we have here. Here we've got a variable density. But the way that it's used to calculate mass is still the same. The density of a piece of an object can be multiplied. The density, in this case the mass density, is simply the mass per, and then here insert whatever you like, mass per, when it makes sense, mass per length, like the example of my ruler. When it makes sense, mass per volume, like my example of the wood block, or sometimes even per surface area, Sometimes, for example, this piece of paper, if I were to chop it into little pieces, squares, triangles, whatever, I would expect pieces of equal area to have equal amounts of mass to them. And if I wanted to figure out the mass of a couple pieces of paper, what I would do is I would calculate the mass per area and then multiply it by the total area of whatever piece I'm holding to figure out the mass of that particular piece. Same idea with length and volume. If I cut off a random piece of this ruler and I wanted to figure out how much it weighed without actually, weighing it on a scale, I could just measure its length, and if I knew ahead of time how much mass existed per length, then I would take that mass per length multiplied by the length to get the density. So in this case, we have a density in terms of mass per volume, so I want to multiply it by volume. So mass per volume times volume equals the mass of an individual piece, equals mass of an individual piece or section of the overall thing. Mass times volume, or not mass times volume, density. Mass density times volume, in this case, would give me the mass of a particular piece. Assuming, of course, that your density was constant. Here, our density is not constant, but we can make it constant if we just minimize the change in R. If we have very little change in distance from the center, then over that very small change, the density will be approximately constant. We can do that. We can slice this cylinder into pieces, or not cylinder, sphere, into pieces. These pieces will be cylindrical shells, which I'm not really the best at drawing, but I'll try my best over here. So let's see. If I were to take this sphere and cut it up into a bunch of nested shells, I'm not sure how I'm going to make this look 3D. Maybe we'll just have to settle for looking at a cross section. If I were to chop this sphere into a bunch of little spherical shells, how am I going to make this feel 3D? I don't know. I feel like I've already messed it up. Yeah, I'm not sure. Maybe if I draw some sort of okay. Let's say that we've chopped a sphere in half and we're looking at the inside of it like this. Yeah, and then this is kind of like a dome in the back. Okay, so we're looking at just one half of our sphere and we're looking inside of it and we're seeing all these kinds of rings, all of these half spherical shells. That's basically what I'm trying to chop this thing into. If I make these shells super thin, then the difference in R from, let's use a different color, then the difference in R from here to here, you've got a different radius here versus here. If I make these shells really, really thin, then the change in R will be so small that the change in density between the inner part and the outer part of this one shell will also be negligible. I will be able to treat my density as if it's being constant, kind of the same way as, again, I'm going to keep referring to this image, as if I'm treating the height of this curve as being just equal to this height of the rectangle for the whole interval. As long as I shorten my interval, that approximation will just get more and more accurate as I go. So yeah, for an individual shell, for any individual one of these shells, I can treat the density as being constant for that particular shell. Then I can say that the mass of an individual shell is equal to the density, which will be constant for that shell, or constant enough, times the volume of that particular shell, times the volume of that particular shell. Okay, density, we can just rewrite it as Kr, so the mass of an individual shell. is going to be Kr times the volume of an individual shell. Well, these shells don't all have the same volume, so I'm going to have to either write my radius variable in terms of volume or write my volume variable in terms of radius. Writing my volume variable in terms of radius is probably the better way to go. So what would be the volume of an individual one of these shells? Let me try and draw one. Let me attempt to draw one of these shells. Let's see, and I'll draw a half shell rather, since that seems to be the best I can do. I'll draw a half shell like this. So I'm just looking at one half of a shell. It's going to have a radius, some random radius, little r. It's going to have some random radius, little r. It's going to have a difference between its inner and outer radius, which is going to be relatively small. We'll make it small the thinner that our shells become, but this difference between the inner and outer radius, I'm just going to do this, two arrows just kind of pinching it. This I'm going to call my delta r. And what I can do to calculate the volume of this shell is I can calculate the surface area of a sphere. I know the surface area formula for a sphere. I would hope that you recognize this. Surface area of a sphere is equal to 4 pi times the radius squared. I would hope this equation looks familiar to you. If not, then you might want to look through your geometry book if you still have it, or I guess there's always Google. The surface area of a sphere is 4 pi r squared. If I take the surface area of a sphere and multiply it by its thickness, that should give me the volume of a shell, or at least the approximate volume. This is kind of the same logic as if I take a brick or maybe not a brick, but like a thin tile of whatever shape. It doesn't even have to be rectangular. And I take the area of that tile's base and multiply it by whatever little thickness it has, this thickness. That would give me the volume of that piece. Kind of the same thing is going on with this spherical shell. This was probably not the best example to start with in hindsight, but we're committed, so let's go through it, and maybe I'll give another example that will hopefully be much simpler than a sphere. I have attempted to give examples with spheres twice this week, and both times it has failed me. I should probably not be looking at spheres for a while until I've prepared a more digestible explanation for how to work with them. Okay. Anyway, thickness multiplied by surface area equals volume for a thin spherical shell. Yes, the curvature kind of adds a twist to it, but remember, we're making these things so thin, we're making this delta r so small that that's not really going to matter. So I guess I'm asking you to rely on your intuition to a great degree today in order to convince yourself that what I'm doing makes sense. I don't have the most rigorous proof for what I'm doing today, unfortunately. I've always kind of just done it intuitively myself, and I've never really had to teach this before, so I guess I'm learning stuff here too. So Surface area of a sphere, 4 pi r squared multiplied by the thickness, volume of a shell, volume of thin shell, is going to be 4 pi r squared times this thickness delta r. Okay, now that I have the volume of a thin shell, I can put it in here. Mass of an individual shell is kr times volume of a shell is 4 pi r squared delta r. And if I want to do this for multiple shells, if I want the total mass equals the sum of the masses of shells I, where I starts from whatever your first shell is, I guess it would be shell 0 up to shell n. It would be the sum from I equals 0 to n of, let's multiply the k and r into this, and that would give us 4 pi k r cubed delta r. And then if I took the limit as n approaches infinity of this sum, then I would end up getting the integral. I would end up getting the integral from the first shell of radius, I guess 0 would be the innermost shell, to the outermost shell, which would be at radius of big R, the full radius of the sphere, times 4 pi k r cubed, and then my delta r would just become a dr. Okay, the 4 pi k, those are constants. I can just factor them out of the integral the same way I can factor them out of this summation. And I'd be left with 4 pi k integral from 0 to big R of r cubed dr. R cubed dr, that will integrate to, well, a cube becomes a 4th power, and then we divide by 4, so that becomes r to the 4 over 4. 4 pi k times r to the 4th over 4, evaluated from 0 to big R. Technically, you can skip this step and just skip ahead to big R to the 4th minus 0 to the 4th, but I'm writing these steps in between just because this is probably new to a lot of people. 4 pi k times, that's just going to be big R to the 4th over 4 minus 0 to the 4th over 4. I probably should not have written all this stuff so close to each other. Let me see if I can use a different color to, yeah, that should make it a little bit more readable. There we go. And then, yeah, 0 to the 4 over 4, that's just gone. And this 4 cancels with this 4, and I get the total mass is equal to pi k times the radius of the sphere to the 4th power. Okay, not really the best example I could have given, but maybe this is something to revisit later once you've had more experience and it'll make sense at a later time. I do not blame you for being confused by this. Let's do, I guess one that would be relevant to physics mechanics would be moment of inertia. And let's do moment of inertia for, how about moment of inertia for a uniform cylinder? Do I have, yeah, the back of that is already covered, so new sheet. Let's calculate the moment of inertia. Let's calculate the moment of inertia for a uniform cylinder or disk. A disk is just a really short cylinder, so they're basically the same thing. Those who may have taken Physics 1 before and are now doing Physics C might have seen this formula in textbooks. You didn't have to memorize it, but moment of inertia for a cylinder or disk was equal to 1/2 times the total mass of the cylinder times the full radius of the cylinder squared. In general, moment of inertia for a mass, for a point mass, is equal to whatever that mass is times its distance from the axis of rotation squared. And for those who haven't done any physics before, this is probably not making any sense, so let's explain this idea. So suppose I have a cylinder over here, and my axis of rotation is running through its center. That's also something I should have specified here. Cylinder or disk with rotation axis through center, Specifying the rotation axis is important. Through the center. And I suppose that's not even the best description, because through the center could also mean, like, you know, this way, but I think my drawing already sufficiently illustrates which rotation axis I'm talking about. I'm talking about this. So a moment of inertia, for those who don't know their physics, basically it's the resistance that an object has to rotation. If I try to rotate something, like if I try to rotate this ruler, if I try to twirl it by holding it from the middle, I don't have much difficulty doing that. It's pretty easy to twirl when I hold it from the middle. It's pretty easy to make it rotate clockwise or counterclockwise. I don't require that much effort. However, if I try to rotate it from its end like this, then I have a much harder time. It would be easier if I used a more rigid ruler, but I don't have that, so I have this rubber ruler that kind of flops. But if you have some sort of rigid stick-like object, try twirling it through its center versus trying to rotate it by holding it from an end, or not even from its end. You could just twirl it, you could try to twirl it from somewhere off center, and it will feel harder than rotating it from the center. And that's what moment of inertia is about. What I'm doing by changing the position that I'm rotating it from is I'm changing this axis of rotation. Basically where my thumb is the axis of rotation that I'm using, and different axes of rotation will allow you to encounter different resistances to that rotation. The most resistance to rotation is encountered when more of the mass is farther from your axis of rotation. So the more mass you have, that I think is intuitive enough. The heavier it is, the harder it'll be to twirl it. But also, where you position your axis will determine this, which is usually the biggest factor. this r thing is the distance from the axis. If I put my axis of rotation in the center, what that means is that the farthest parts of my ruler, the farthest parts of this ruler's mass, are at the minimum possible distance they could be. Because if I grab the ruler from further, like here, then the mass at this end of the ruler is, what is this? Let me see. I'm holding at 7 centimeters, and that's at approximately 30. So right now, the farthest parts of this ruler's mass are 23 centimeters, 23 centimeters away from my axis of rotation. Whereas if I hold it from the middle, the farthest pieces are only 15 centimeters away. So yeah, if I minimize the distance of the farthest parts of an object, that will usually reduce the amount of effort I have to put in to twirl and rotate that object. So that's what moment of inertia is for those who haven't learned the physics yet. So for a point mass, if this ruler, actually, you know what, forget the ruler. Let me grab a dumbbell. I don't even know if this thing is going to show up on the screen properly. I don't know if it will completely fit, but look at this dumbbell. Yeah, that doesn't fit completely on the screen. Oh well, we'll work with it. Is that better? I suppose. So with this dumbbell, you've got a smaller part of the mass is over here in the middle, and most of this mass is going to be really close to the axis of rotation if I try to rotate it, from the center of the actual bar part of it. But then you've got these two different lumps of mass that are pretty much entirely, let me see, what does my ruler say? How long is this thing? This thing is this central bar is about 15 centimeters long. So yeah, I've got these two little lumps of mass that are 15 centimeters away from this axis of rotation. So if I treated the masses of these two lumps as being at a single point, I would say that the mass is at a point that's, let's see, if this was 15 centimeters, then I would say, and let's pretend that the mass of this central part is mostly in these two lumps as well, then I would say, what is this? Is this a 15 pound? Yeah, this is a 15 pound dumbbell. So I would say that half of my 15 pounds, so I would have a mass of, let's see, it would be 7.5 pounds divided by whatever g is supposed to be in imperial units. That would be the mass of one of those two lumps. I would multiply that by, what was the distance? It was 7.5 centimeters. I would have to convert that to correct units as well. And then I'd have to square that. And then that would be the moment of inertia for one lump, for one point of mass. And then I would also have to add the second lump. So in this case, I would have to just multiply by 2. But in general, the moment of inertia for a rigid object that contains its mass at more than just one point, the moment of inertia for a rigid object is actually the sum of each little bit of the object's mass times the distance of each bit squared from the axis of rotation. And you would just have to sum those up. But this is the base formula that we would start with. Let me put this dumbbell away. I didn't mean to turn this into a physics lesson, but I imagine a lot of physics students will be interested in this topic anyway, so perhaps that's a good thing. Wait, don't want to use this color, I've already used it enough. Let's see. So, what was I trying to say here? So yeah, basically, I'm trying to work with this. I want to chop this cylinder up into a bunch of little pieces, and I want to do that in such a way that I guess the most critical variable here would be r, this r thing. I want this to be approximately constant from piece to piece. And the ideal way to chop this up then would be not too different from what we did with the sphere, actually. I want to cut this cylinder up into a bunch of cylindrical shells. This is going to work very beautifully for us because of rotational symmetry. If I chop my cylinder up into a bunch of cylindrical shells, this is going to work really nicely because I can, if I make my cylindrical shells thin enough, then their radius will be approximately constant, and that would mean that all points within an individual shell will be the same distance away. So then the moment of inertia for a particular shell is just going to be the mass of that shell times the radius of that shell squared, times the radius of that shell squared. And then if I just do this for each and every shell and I add them up, there you go, I would get the moment of inertia for the whole cylinder, or at least an approximation for it, unless I take an infinite number of these shells and make them really razor thin. Okay, so that's great and all, but how do I know how much mass is contained within a shell? We said that this is a uniform cylinder, so the mass is distributed evenly per volume. So the outer shells are going to be obviously bigger than the inner shells, and when an object is uniform, the bigger its pieces, the more mass those pieces contain. So I need to come up with a formula to figure out the mass of an individual shell based on its size. And for that, I need to actually figure out what the size of a shell is. So let's take one of these cylindrical shells. I did this before, I think like 4.5 years ago in one of my AP Calculus review videos. If we take one of these cylindrical shells, say you take like an empty roll of toilet paper and you grab some scissors and you cut this thing open and you unfurl it. Let's say I take some scissors and I cut this thing open and I unfurl it, and I'm going to lay it sideways. So I begin to unfurl it. Maybe first it looks like this when I first open it up. And then I guess I would have to, let's see, draw something like that. I think I messed up this drawing really badly already. Yeah, I think I've already messed this up. Okay, actually no, I think I've saved it. let's say I start unfurling this thing, opening it up, and then so, I don't know, cut it along this line, cut it along this dotted line with some scissors, and then start opening it up. Eventually, you unwrap it, and it ends up looking something like this. Okay, I think I messed up that part. Yeah, I feel like I'm missing a line somewhere in the front of this thing. Just goes to show how important art skills are for teaching. But yeah, if you unfurl this thing and you open it up, you can make it kind of flat. It'll still have a little bit of curvature to it because the thickness is not negligible. You'd probably have the easiest time doing this with something as thin as the cardboard of like an empty toilet paper roll. I think that would be the best example that you can play around with at home. But yeah, take some sort of cylindrical tube thing, cut it open from the side, and unfurl it, and you can mostly flatten it until it ends up looking approximately like a square or rectangular tile. Until it ends up approximately looking like some sort of square or rectangular tile. Okay, what's the volume of this thing? Well, this would be just the area of its base times whatever this is, whatever this height is. That would be its volume. So for the area, I would just take whatever this length is, L, and multiply it by whatever this width is, W, and yeah, length times width times height. If you make your cylinders thin enough, then there's little difference between this curved shape that's not quite a rectangular prism and this thing, which is a rectangular prism. When you're dealing with really, really thin shells, the difference just disappears. So let's figure out what these length, width, and height are. Well, the height is just going to come from here. Whatever the original thickness was of the cylinder before I unfurled it, that would be this, which becomes this, which becomes this. There you go, that's the height. Okay, the width is what used to be the length. This used to be this before I ended up cutting along my dotted line. Becomes this, becomes this. So the width is just the original height of my cylinder. So the width, I guess if I call the height of this cylinder capital H, then the width is just going to be equal to that capital H. Speaking of which, I forgot to define this. This I'm going to call a small change in R delta R. I think you can see where this is going. That's going to turn into our differential. And then what about the length? The length, let me use a different color for it. How about purple? So the length is what used to be this. This, all the way around this circle. That, when you open it, turns into all of this, which turns into this, which turns into our length. And what was this before we unfurled it? If we treat the radius if we treat the inner radius and outer radius as being approximately the same, then we can just take whatever radius this particular shell had, whatever radius our shell we had. That's not even legible, is it? It says our shell. You're just going to have to trust me on that. If we take that radius, we can just use 2 pi r to calculate the circumference of this shell. And so that 2 pi r unwraps into this, then gets flattened into this, and ultimately gets flattened into this. So this length is equal to 2 pi r. So the volume of a shell, V of a shell, is equal to length, 2 pi r, times width, which is capital H, times the height, which is delta r. Okay. Now we can get the mass of a shell, because the mass of a shell is equal to the density times the volume of a shell. And when an object has uniform density, the density formula for a uniform object is simply the total mass over the total volume. The total mass, we'll just call it big M. I forgot to specify that. This cylinder has a total mass of big M and a maximum radius big R. So total mass, that's just a given. Total volume, we can write it as, let's see, density equals M over total volume for a cylinder would be pi r squared H. Pi r squared H. And so now we can get the mass of a shell. I guess I'll do it down here since I'm running out of space. Mass of a shell is equal to density, big M, over pi r squared H, times volume of a shell, which we just got, 2 pi r big H delta R. 2 pi r big H delta R. And here we see why the height, whoops, canceled the wrong thing. Whoops, no. The pi looks like an H. Sorry about that. And we see now from the H canceling out why the height does not factor into the moment of inertia formula for a cylinder that you see in most textbooks. So we're starting to see more and more of how we are supposed to get here. Come to think of it, actually, it was not such a bad thing that I crossed out the pi, because the pi also cancels out. Yeah, the pi cancels out with this pi over here. Okay, the day has been saved. So that's the mass of an individual shell, and I want to now put that into my moment of inertia for an individual shell, and then I want to sum those up. So the moment of inertia for the whole cylinder, the total moment of inertia, is going to be the sum of the moments of inertia of a bunch of shells. Is going to be the sum of, let's see, the mass of an individual shell is, we've got the 2 and the m and the little r, 2m little r over big R squared, and then delta R, that's all that's left out of that. So that's the mass of an individual shell, times R squared, and these R's are the same. They're just the radius of a particular shell. I guess we could call these Ri if we want to stay true to the summation notation. And we can just use our intuitive translation from sums to integrals. This is just going to become I total equals, if we make this an infinite sum, is going to be equal to the integral from, I guess we'd start at a radius of 0 to a radius of big R. Well, let me not get ahead of myself. We'll talk about the bounds in a minute. Let's copy over what we have. So we've got 2m over big R squared, and then we've got this r and this r squared. That's going to become r cubed, and then the delta r is going to become our dr. And then we're going to have our integration bounds. Since we're integrating with respect to r, we're going to go from r equals 0 to r equals big R. The radius of our, let me separate those so that they're easier to read. So the radii of our shells, we start with a shell of radius 0, so I guess an empty shell, and we move to shells of bigger and bigger radius until we hit the last shell at radius big R. That's the progression. That's how we are stacking our shells. Okay, the 2 and the big M and the big R squared, those are all constants that can be factored out. We would just be integrating r cubed dr, and that would be increase to 4, divide by 4. In fact, I don't even have to bother with factoring out. Let me switch colors and see if I can fit this down here. m over big R squared times r to the 4th all over 4, evaluated from 0 to big R. If I plug in 0, this is going to give me 0. And now that we've seen this, 3-4 times now, you might think when the bottom bound is 0 that you can just ignore it, but it really depends on what function you get. So don't be too quick to write off this step of the problem. There will be times where that 0 is actually going to give you something that matters. Anyway, 2m over r squared, or I guess over 4r squared, I should say, times big R to the 4th minus 0 to the 4th. Okay, the 0 is gone, and then we've got 2 over 4 reduces to 1/2. Oh, the m just stays as is, and then r to the 4th over r squared is r squared. Would you look at that? Exactly what we were supposed to get. Okay, I think this might be a good place to leave things for now. I think the best thing to practice if you're a complete beginner, the best thing to practice would be kind of similar to what we did in the first example with dividing a cone into a bunch of disks. You can prove the volume formula for a pyramid. So that is a challenge that I think you can handle. See if you can come up with the volume formula for a pyramid. And it doesn't even matter what kind of pyramid it is. It doesn't matter if it's a square pyramid or a triangular pyramid or a hexagonal pyramid or whatever, but I would recommend that you just start with square pyramids. Those would probably be the easiest for you to deal with. So yeah, a challenge for you, challenge yourself, and see if you can prove to yourself using integration that the volume of a pyramid is 1/3 of the base times the height. 1/3 the area of the base times the height. It should be quite similar to what I did with the cone. Maybe you can find a more streamlined process than me, because I'm not entirely happy with the way that I explained things today. I was even mentally rehearsing and everything all week, and I thought I had a very smooth way of explaining things, but yeah, I'm not entirely satisfied with this. I'm gonna think about this more and see if I can explain it better the next time I have to discuss this topic, which might be sooner than you think, because I feel like we might be able to use some more examples of this. But that remains to be seen. I most likely will be switching to a different topic next week. I don't know what that topic will be, but I wouldn't say I've entirely written this topic off quite yet. I feel like there's still a need to cover more things here. I just don't know what yet, and even if I did know what, I'm gonna need time to figure out how. This is the curse of intuition. When something is so intuitive to you that you kind of just did it without thinking about it and you don't know how to explain it. Well, I will worry about that on my own time. Hopefully, this has been helpful despite the admittedly confusing explanations. Hopefully you got something out of this just through sheer exposure to examples. Hopefully something clicked, but if things aren't quite clicking yet, I'll be reflecting on this and seeing if I can come back with a better way to go over all this stuff. Anyway, that's it for me. Take care, and I will see you in the next one.